Sure.
What's up, you scholars of enlightenment? 2 weeks ago, Stanford astrophysicists reported the first detection of light from behind a black hole, a development that might allow us to further probe the incredibly hostile environment around these space-bound Goliaths, and which fulfills yet another prediction of Einstein's theory of general relativity. So I'm incredibly pleased to say that we have one of those Stanford astrophysicists, Professor Dan Wilkins, with us today to help unravel those recent results. Professor Wilkins, welcome to the show.
Thank you, Sam. Pleasure to be here.
Thank you very much for taking the time. You've obviously been very busy recently. So Professor Wilkins is a research scientist, astronomer and astrophysicist at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. And his research focuses on how material spiraling into supermassive black holes in the center of galaxies power some of the brightest objects we see in the universe. And he uses these X-rays that are emitted from black hole flares and corona to create 3D maps of the extreme environment just outside the black hole event horizons. He's also incredibly passionate about science communication and communicating science to the public. So who better to help us unravel this intriguing topic? So, Professor Wilkins, before we start, it would be remiss for me not to explore our Cambridge connection. So, your website says that you got your PhD from Cambridge in 2013, which is basically the same time I got mine. You were in the astronomy department. I was apparently 50 meters away in the particle physics department on the same floor, and yet we didn't run into each other. What's going on?
Yeah, so I was actually based in the building just across the street from the physics department.
Now it all becomes clear, right? So it's not my fault of being a hermit and not going out and talking to anyone, possibly.
They managed to complicate things in Cambridge. They actually had 3 different departments that do astrophysics for some historical reason that I'm sure nobody quite remembers.
I guess you were over the road with some of the mathematics as well, were you, at some point?
Yeah.
So lots of that going on. Did you ever meet, I don't know if you ever met Jalal or Carl, who were a couple of my friends in the astrophysics department? Perhaps not.
I know the names.
You know the names, but you didn't meet them. Right. Okay, fine. That's good. At least I get into the orbit a little bit. So, given your interest in these fascinating topics and science communication, I'm kind of annoyed, I'll admit, that we didn't sort of chat sooner, but let's move on to today's discussion. So, first question. How did you get into this research area and trying to understand the environment around black holes?
So I guess, physics has always been something that interested me. I guess this is something you can relate to as well. Like, I've always been trying to understand how everything works, whether it's like technology, our environment and stuff in the universe. So that led me into an undergrad degree in physics. And it was during my undergraduate that I started exploring topics in astronomy and astrophysics. And as part of that, I discovered this really amazing galaxy that's called Cygnus A. And this galaxy really stood out to me because if you look at it in visible light, it's a fairly unremarkable galaxy. It's a little bigger than most, and it's got a few things going on that you can see, but nothing that really sets it apart. But if you look at this galaxy in radio waves instead of in visible light, you see that there's something right in the center of this galaxy that's shooting out these enormous jets of particles traveling at almost the speed of light that extend far out of the galaxy. And these jets are being launched by the black hole in the center of that galaxy. And I just thought to myself, that is really amazing. I need to figure out how that black hole is doing that.
It sounds an incredibly cool thing because I guess people tend to have that concept of a black hole draws everything in, nothing escapes. But actually, these are some of the brightest X-ray sources we have, and some of the brightest objects, full stop, that we have in the universe. And perhaps people don't realize that. Is that fair to say?
Yeah, it's kind of a weird paradox when you think about it. Like this black hole that's got its name because anything that goes in, including light, can't come out. And that actually holds true. We're not seeing light coming from inside the black hole. What's happening here is there's gas and other material that is falling into these black holes at an enormous rate. And as that gas falls into the black hole, it gets heated to exceedingly high temperatures. And it's this superheated gas in its final moments plunging into the black hole that's producing all of the X-ray emission and the light that we're seeing.
So why do we have such an interest in these supermassive black holes at the center of galaxies? Why are they so important, and what can they tell us?
So there's a couple of things going on here. So we think that every major galaxy in our universe, that is to say, not the little dwarf galaxies like the Magellanic Clouds that we're still not sure about, but all of the major galaxies, as far as we know, have a supermassive black hole in their center. And this is a black hole that is somewhere between 1 million, 1 billion, maybe even tens of billions times the mass of the sun. And even our own galaxy, the Milky Way, has got a supermassive black hole in its center called Sagittarius A star. And our black hole is pretty quiet. It isn't swallowing large amounts of gas. It nibbles on little bits of gas every now and then and produces little flashes of X-rays, but nothing too major. But we're looking at supermassive black holes that are swallowing gas at an enormous rate. And the energy that's released when this gas falls in is enough to power actually the brightest continuous sources of light in our entire universe, as far as we know. I say continuous because there are things like supernova explosions that get brighter, but they fade away after they've gone off. But these things are the brightest continuous sources of light. And if you just do a simple sum of all of the energy that's coming out of this black hole, whether that's in the light or it's the kinetic energy in the jets that I spoke about earlier, you add all of that up, it turns out that it's more than the gravitational energy that is holding the stars in a galaxy together.
Wow. So an incredible amount of energy. So is the idea with supermassive black holes not only that they're these amazing sources of energy, but is there a link to them to the basic formation of a galaxy as well? You were saying they're in the center of all galaxies. Are they essential for having galactic formation, or is that going too far?
So one of the breakthroughs in the last couple of decades is that, yes, these black holes aren't just ornaments. They really do play an important role. Because the energy coming out is more than what holds the stars into the galaxy, that's telling us that the black hole can actually play an important role in how that galaxy formed. And the way we can think about this, if we imagine a galaxy growing in the early universe, the galaxy grows as gas falls into it. The force of gravity draws the gas in, and that gas eventually clumps up and forms the stars in the galaxy. If we've got this black hole that's growing at the same time at the center of that galaxy and spitting out enormous amounts of energy, as the gas is trying to fall into the galaxy, this black hole in the center is trying to push that gas away. So you can
there's a radiation pressure in the opposite direction. Is that the idea?
Yeah, exactly right. It's the radiation pressure and even just the jets, the mechanical power of the jets pushing on the gas as well. And we think that it's this black hole that's stopping the galaxy growing too big and sort of shutting off the formation of the galaxy. So really understanding what this black hole's doing is a really important component in understanding how the galaxy that we live in and how the galaxies that we see became the way they are today.
Amazing. And in your recent research, you've taken to looking at a black hole in the, I don't know if it's Wonnes-Vicky-1 or Elsvicky-1 galaxy. Wonnes-Vicky-1, which is a galaxy about 800 million light years away. Now that sounds like an incredibly large distance. It is an incredibly large distance. Why did this particular supermassive black hole grab your attention? Is it particularly noisy? Is it different in some way?
So yeah, there's a couple of reasons. One of them is actually, you said it's a long way away, which 800 million light years is a long way away. But as far as galaxies go and supermassive black holes go, 800 million light years is actually pretty nearby.
It's all relative. It's always relative.
Yeah, but that works in our favor because it's nearby. It appears that just that much brighter because it's closer to us, and that means we can get a really detailed look at it with our telescopes. And as you said as well, it's a little noisier than most galaxies and most black holes. We think that even though the actual mass of the black hole is pretty modest, it's about 10 million solar masses, so it's a couple of hundred times smaller than the biggest black holes we've ever seen. It's actually feeding on gas at a slightly higher rate, and this means that as well as being nearby, it shines and it's very noisy, it's very unstable. So it's not just a constant source of X-ray light, it's sputtering, it's emitting flares, it's getting brighter and dimmer all the time. And this is giving us a lot to study, a lot to look at, to really understand what's going on and the processes that are producing those X-rays.
And this is going to become very important in the analysis, the specific analysis that we discuss shortly. So it's close in cosmological terms, quite bright, and it's also sputtering. So it's a very useful one to look at. How are we looking at that black hole? Obviously, in terms of looking in the sky and with visible light, it's very, very small in the sky. What instruments are we using? What techniques are we using to look at that black hole?
So there are lots of different ways we can look at black holes, and we can take advantage of all the different wavelengths of light or electromagnetic radiation to study them. We can use radio waves, submillimeter, infrared, visible light, ultraviolet, all the way up to X-ray and gamma ray. And we were in particular looking at the X-ray emission here because the X-rays give us a really good view of what's happening to that gas that's right around the black hole, that's just about to fall in. And to do that, we have a couple of X-ray telescopes in orbit around the Earth. So X-rays can't travel through much air, so it's pretty useless to put an X-ray telescope on the ground. It just won't see anything. So we put these telescopes on satellites, and one of the satellites we were using is called XMM Newton. It was launched by the European Space Agency in 1999, and it's actually about the same size as the Hubble Space Telescope. It just looks at X-rays instead of visible light. And alongside XMM Newton, we were actually simultaneously looking at the same black hole with one of NASA's telescopes called NuSTAR. And NuSTAR is a little bit smaller, but it's able to look at slightly higher energy X-rays that are really good for looking at the X-rays that reflect off of the gas falling in.
So those two telescopes, there's NuSTAR and there's XMM Newton. They look in the X-rays, but at slightly different wavelengths of X-rays. Is that correct?
Yeah, exactly right. XMM Newton looks at the slightly longer wavelength, lower energy X-rays, and then NuSTAR is able to focus higher energy X-rays. So we can just get that broader view of the spectrum by combining the two of them.
Makes sense. A nice complementary measurement there. So in the latest research, you were observing, as you kind of alluded to earlier, flares or corona from the black hole. What are these corona? What's the best explanation for how they form and why we see these incredibly bright events in the sky, and why are they so important?
So the sort of cartoon picture we have here is that the gas that's falling into the black hole ends up flattening down into a disk. We call it an accretion disk, that's the technical term. But we can kind of just think of this as a flat disk of gas that spirals around the black hole, working its way in, kind of like water going down a sink. But this gas, as it falls in towards the black hole, is getting crushed together by the immense gravitational force from the black hole. And this causes that gas to get heated up to millions of degrees. So this gas isn't so much a gas that we're used to here on Earth. It forms a plasma. It gets so hot that the electrons fall off the atoms. and you've got this this plasma, this superheated gas moving around in orbits around the black hole. And if you have electrical charges, those electrons that have come off moving in orbits, that's essentially an electrical current.
Yeah.
And an electrical current generates a magnetic field. So you've kind of got this giant electromagnet around. Not only that, but the electromagnet, the disk of gas, is spinning around. The black hole in the center is also spinning.
Yep.
And this means that the lines of magnetic fields that get generated get tied up into knots.
Yep.
And when that happens, they can undergo a process called reconnection. That's kind of the same process that powers solar flares, just on a much bigger scale. So you have the solar corona, these ejections coming off the surface of the sun. We think we're looking at the same process scaled up, which is why we give what's going on around the black hole this nickname of the corona. Just this
we've heard so much corona this year, but this is, specifically astronomical phenomena. There's no link back to people having flashbacks of this year.
Yeah, it's slightly unfortunate putting this paper on now. Corona's the last thing we need to think about. But yeah, essentially what's happening is what we think's happening is the magnetic field is getting tied up into these knots around the black hole, and this is accelerating the electrons to extremely high energies. It's dumping energy into these electrons. So very close to the black hole, we're getting this very high energy group of electrons, and those are what are producing the bright X-ray emission that we're seeing. But actually, a lot of how the corona is formed is a mystery. We're still trying to understand exactly where it is, how big it is, exactly how it gets formed by the gas falling into the black hole. And that was actually one of the primary goals of this study. It's one of the things we're looking for in One's Wiki 1 is to get more evidence to try and figure out exactly how this corona works.
Interesting. So the light that we see in our telescope, as we go more into the specific analysis that you did for this Nature paper, the light we see in our telescope coming from the black hole, from the corona, it seems to be a mix of two sources. It's light that comes directly from the corona to our telescope, and also light that can come down and bounce off the accretion disk that you talked about so eloquently, and then reflect to our telescope. Is that correct?
Exactly right, Sam.
Good. Right. I did get it right, and I understood. So the question becomes, how can we, because this is the focus of the entire paper, how can we separate that light out? How do we know that it's light that's coming directly to us and light that's bouncing off of the disk? How can we do that separation?
So we've got a couple of tricks up our sleeve to do this. And this is something that I've been working on with many of my collaborators now for a number of years. And so the real key here is that when the gas in the accretion disk reflects the X-rays, it doesn't just send back exactly the X-rays that hit it. It's not a true mirror in that sense. When the X-rays hit the gas in the disk, some of them will be absorbed by the atoms in the disk. And when they get absorbed, the atoms will then re-emit the X-rays, but at very specific wavelengths or very specific colors of light. And this is exactly the same phenomenon if you look at a street lamp that has a sodium bulb in it. Street lamps produce a very specific color, that yellow color. Yep. And that is the specific color of light that is emitted by the sodium atoms in the bulb. And in exactly the same way, the different chemical elements in the disk emit light at very specific colors. And some of those elements, the colors they emit, won't be visible colors of light. They will be X-ray colors. Yeah. So we're looking at light that should be emitted from the disk at a very specific color. And the really useful atom for doing this is iron. Iron atoms in the disk produce a very strong signal.
And you were saying, so we can probe the disk using this this iron line. So essentially, it seems to me like in this paper, the corona sort of acts sort of like a lamp, which is hanging above the accretion disk, if you will. And then the light shines down and bounces off it. How can we determine the places that were struck by light and where the light's coming from? How does it change that light that bounces down into the disk, particularly that iron line that you mentioned?
So this is an idea that actually goes back to the late 80s, and my PhD supervisor, Andy Fabian, along with Martin Rees and others, were thinking about what happens to and they're called emission lines, these specific colors of light that come from the chemical elements. But there's so the iron in the disk emits X-rays at a very specific wavelength or color. But that's not the wavelength that we observe those X-rays at. The color that we see actually gets changed by two different things that are happening around the black hole. The first thing is just the motion of the gas. So the gas is traveling around the black hole in orbits. And by the time you get to the very last orbit, before the gas falls into the black hole, the gas is traveling at half the speed of light. And when gas is traveling that fast, the light that it emits gets Doppler shifted.
Yeah.
So the light waves that are coming towards us get shifted to a shorter wavelength or to a bluer color. And the gas on the other side of the disk that's moving away from us will get shifted to a redder color.
So we might have started off with a nice sort of Dirac spike of a spectral line for iron, but now it's getting smeared out on both sides. One where the disk is moving towards us, one where it's moving away, and we get this sort of spreading out. And I've got up the nice diagrams that you have of how the sort of line gets spread out into these weird and wonderful shapes by the effects that we're talking about.
Yeah. And then if you look at the low energy part of the line, the red side of the line, it's got that long extended wing on it.
Yeah.
There's that's actually the second effect that comes in, and that's the black hole. So the gravitational field around the black hole is really strong. And when light climbs out of a gravitational field, it also gets shifted to longer wavelengths or redder colors. So you get the blue spike and what would be a red spike from the motion of the gas in the disk. But then because all of that light is having to travel out of the strong gravitational field, it's getting stretched out to these really long wavelengths, producing that long wing on the line.
So depending on where the light hits the disk, these effects of the gravitational strength of the black hole, which I guess the effect gets bigger if you hit closer to the middle, and also this spin of the black hole, depending on if you hit on the left or right of this diagram. Obviously, it's projected in space towards the Earth. Depends on the energy shift we'll see in that light. So, depending on the energy shift we see, we know where that light potentially came from on the disk. Is that fair?
Exactly right. Yeah, we can, once we know what color we see the light and what color it should be coming from the iron, we can start to figure out whereabouts on the disk it came from.
So this is you've got this beautiful model. So I'm showing people the images that your model has as what we would expect to see from this iron K line, if this model is correct, where you have a point like corona hanging above the black hole, it's shining light down onto the disk, and that disk is reflecting the light back to our telescope, and we expect all these weird and wonderful shapes for that iron line in different windows of energy. All makes sense. The question is, how does that model fit with the data that we have? Do we see that model, that beautiful model that you have, reflected in the data from the black hole? Because that's always the big question, I guess.
Yeah. So there's a number of...
Seeing as you have a paper in Nature, I'm guessing that we do.
Yes. I think, yeah.
So what does that data look like? I'm going to bring it up, actually, so people can see it as well. How can we be certain that that iron line that you've predicted in your model is what we're seeing in this data?
So the real key here is putting together all the different pieces of the puzzle that we have. So the first thing we want to do is we want to make sure that we're actually seeing this ion line from the disk in the first place.
Yeah.
So the first piece of evidence that we have is that we just look at the spectrum and we see that beautiful broadened shape of the ion line with that long wing of the emission coming from close to the black hole.
Yeah.
And then before we even look at the flare, I mean, this corona is flickering all the time. Yeah. And every time the corona gets brighter, the reflection from the disk should also get brighter.
Yeah.
But there'll be a time delay between the corona getting brighter and the disk responding to it. And that's due to the just the time it takes the X-rays or the light to travel from the corona to the disk.
Yeah. So please continue.
And I think what we can do is we can look at all of the observations we've got of this black hole, and we can look at the specific X-ray wavelengths of that ion line, and we can look at the wavelengths that we expect to see coming straight from the corona, and as well as measuring the shape of the line and the shifts in the colors, we can also see the time delay. And that time delay that we can measure exactly corresponds to the distance we expect between the corona and the accretion disk. So that means we're pretty sure we're looking at an ion line being reflected from a disk around the black hole here.
So by taking into account the time delays we would expect to see by the time the time it takes the corona to shine on different parts of the disk, and also the energy shifts that we'd expect from that given point of the disk, putting them all together, this is exactly what we would expect to see in our spectrum, and that's what we see. So we can be pretty damn sure that this is reflections from the disk. So the sort of killer question becomes, actually, before we get to that, why did we pick the iron K line, and would it have been possible to check these results with any other lines? Is it that the K, there's a lot of iron content in the disk, and it was a natural thing to suggest it has the right energy spectrum, or is there anything more intelligent than that?
So there's two things that work in our favor with the iron K line. The first one is that it's a really strong line. So for whatever amount of iron you've got in the disk, it produces a strong response when you illuminate it with X-rays. And the other thing we have in our favor with the iron K line is that it sits on its own in the X-ray spectrum. There are very few other lines around it. And this is really critical. If we're looking for this wing of the line and we're trying to see how much emission is coming from different bits of the disk, it's really important we can accurately see the shape of the line. Yeah. There are lots of other X-ray lines that come out at lower energies. There's another line from iron called iron L, and then there are lines from elements like oxygen and nitrogen. But they're all very close to each other in the spectrum. So if you imagine taking all these lines and stretching them out and putting this big wing on them, they all start sitting on top of each other. Yeah. So it's much more difficult to tell, is that redshifted iron L emission from the inner disk, or is that oxygen coming from further away? Yeah,
that makes sense. So it's a nice isolated line. There's a reasonable amount of iron, and it has a strong response, a kind of, I guess, a cross section for how much light comes in to how much light you get out. So it's a sensible thing to use. And one other thing I wanted to ask before we sort of get specifically into this, or specifically into the echoes from behind the disk, what assumptions do we have to put into this model to get out the results that we have? Do we have to assume the mass of the black hole or the height of the corona above the disk? What assumptions go into this model which we might be slightly concerned about, if any?
Yeah, so there's a couple of assumptions we're making here. And the biggest assumption is that we do have a nice, neat disk of gas around the black hole. The specific shapes of the lines that we're calculating and comparing to the data are assuming that the gas is essentially traveling in circular orbits, and it's pretty much all in a single plane, and it's flattened down. Now, our simulations of gas falling into black holes tell us that this is a fairly reasonable assumption to make, so long as the black hole isn't too greedy. If the black hole is swallowing gas at too high a rate, the amount of energy that comes out superheats that gas. And that the radiation pressure that we spoke about earlier from the gas falling in actually pushes out on the disk. That causes the disk to inflate, and it can cause, instead of the gas following these nice spiral trajectories around the disk and into the black hole, the gas on the surface of the disk can actually be blown outwards like a wind.
So it sort of destabilizes those closest in orbits.
Yeah. So we need the black hole not to be too greedy. It needs to be accreting less than about 50% of the critical rate at which that radiation pressure completely overtakes the gravity of the black hole. And that's something we call the Eddington limit. It also has to be feeding enough. So the black hole in the center of our galaxy is feeding at a very low rate. And when the gas is falling into the black hole too slowly, it actually doesn't shine enough, and that means the gas doesn't cool down and it doesn't flatten into the disk. So the disk puffs up if it's feeding too quickly, but also if it's too slowly, it will puff up and it won't flatten down into that neat disk.
Which probably answers the question as to why we haven't done this analysis on our own black hole. Is that fair?
Exactly right. The gas around our own black hole, I mean, we do see X-ray emission coming from it, but there's not a dense, thin accretion disk, so we don't see a strong reflection signal from it.
Makes sense.
But then the other things you spoke about, like the mass of the black hole, isn't such an important factor in this model, because it turns out that the energy shifts or the wavelength shifts of the light emitted from around the black hole, as well as the velocities of the orbits that cause the Doppler shifts, the mass of the black hole actually exactly counterbalances the expansion of all the size scales.
Yeah.
So a black hole that's 100 times bigger in mass also has an event horizon 100 times larger in radius, which means the like-for-like positions around the black hole where the disk is going to form will also be 100 times bigger. And this means that if you're looking at a disk of gas falling into a supermassive black hole like we were looking at, or if you're looking at a disk of gas around a stellar mass black hole that we find within our own galaxy, and these are the black holes that form when massive stars come to the end of their lives, the range of energy shifts that we see here are the same. So the shape of the line and the range of colors, the range of wavelengths we see in the line, we actually expect to be the same regardless of the mass of the black hole. And the only place the mass of the black hole comes in is determining the absolute size scale. So the corona might be a few times the radius of the event horizon above the disk.
Yeah.
But that can be the difference between maybe 10 miles around a stellar mass black hole and 10 million miles around the supermassive black hole we're looking at.
Yeah.
So that means the time it takes light to travel is going to be millions of times longer around the more massive black holes. But this means actually the mass isn't an assumption we have to put in. We can actually combine the measurement of the energy shift with the time lag we measure, and that actually gives us a handle on the mass of the black hole. It gives us another way of weighing a supermassive black hole in a distant galaxy.
So we can let that mass actually float in the fitting of the model, and it gives us a measurement for the mass of the black hole, which I assume is consistent with gravitational measurements and such in the region.
Yeah, exactly right. I mean, it was. I was very happy when I ran through the analysis.
I bet you were.
Black hole mass that was pretty much on the nose of the estimates of the black hole mass that are made from other measurements of the galaxy. So you can estimate the mass of the black hole by looking at the orbits of the gas and the stars that are further away from the black hole. And I mean, you get pretty big uncertainties on these measurements, but within those uncertainties, the mass we get from fitting these echoes was completely consistent with the mass you get from looking at the dynamics of the gas and the stars in that galaxy.
It's always nice when you fit a model and it's consistent with previous measurements before you go any further. So the one thing before we get into the echoes is there any other possible mechanism that could explain these peaks that we see, rather than it just being reflection, reverberation off the accretion disk? Is there any other potential mechanism that leads us to any uncertainty as to this is what we're seeing?
Yeah, so that's a really important question. Making sure that not only does our model fit the data that we've got, but we also need to rule out, at least to some degree of certainty, any other model that could produce the same observations. So in our paper, we work through the analysis of a couple of different models. And there's a couple of things that could maybe be tricking us here. So if we ignore the time delays for a moment and we just look at the iron line in the spectrum, the energy shifts of the line, there are ways to mimic that if you have gas around the black hole that is absorbing the X-rays coming out. And that can produce shapes in the spectrum that look a little bit like that iron from the disk. But by making a second measurement of those time delays, so by having the spectrum and the time delays, that means we can rule out that other model. The absorption of X-rays in clouds around the black hole can't easily predict the time delays that we're seeing here. And then, and I guess we'll come to this more when we talk about the echoes, but what we essentially saw in the echoes coming from behind the black hole were these very short peaks of X-ray emission. So as the flares were fading away, we saw these extra little flashes of X-rays coming out. Now, if the black hole had just launched a single flare and then it had gone quiet and we were just seeing a pure reflection, it would be easy to see that. But we're actually looking at these echoes of the X-rays from the disk on top of this source of X-rays that's constantly changing, constantly flickering. So there is a risk that actually these extra short flashes of X-ray emission aren't echoes coming from the disk. It's just a short flash coming from the corona. But the information we have that tells us that can't really explain what we're seeing are the specific colors of the echoes. The fact that we saw the echo at a different time and it was slightly different color at each time it appeared. Yeah. And the corona itself emits X-rays over a very broad range of wavelengths. So any rapid variability there we expect to be simultaneous in all the different wavelength bands, and that's not what we saw here. And then the final thing, it could just be random variations. We're looking at a random process, and that means we've got the random changes in the corona itself, but also our telescope is trying its best to collect photons and count the photons that it's seeing. And the photons will essentially arrive in our telescope at random times, that process called Poisson noise. And that can also mean you get variations in different wavelength bands appearing at different times. But we actually have pretty good mathematical models of how the corona varies and how the Poisson noise should operate in the telescope. And that means we can never be completely certain in science like this because we're looking at what is fundamentally a random process. But based on our mathematical understanding of how the black hole varies and how the arrival times of the photons get randomized as they come into the telescope, we can say that the chance of these random processes mimicking the echo signal is less than 0.01%.
Superb. So very high degree of accuracy, and we can be, well, as certain as we can be that these are from reverberations from the disk. So that the sort of thing that has got maybe a bit more of a sort of pop sci attention about this has been the idea of being able to see light that has bounced back off the accretion disk from behind the black hole, been wrapped all the way around the black hole, and essentially is allowing us to see the back of a black hole, which is something we haven't been able to at least separate out before. How when we're looking at these these results, can we tell that we're definitely seeing light from behind the black hole? We're seeing the back of that accretion disk.
So the key here is that we were looking at these bright X-ray flares. And then as the flares were fading away, I noticed in the data there were these little flashes, these little bright patches in different wavelengths that appeared at different times as the flare faded away. And these are kind of puzzling, as we just spoke about. It's difficult to explain this by any other process that we can think of going on around the black hole. But one thing my colleagues and I have been working on for a while are these models of how X-ray flares echo off the disk of gas going into the black hole. And the reason we've been building these models is because we want to be able to measure these echoes and use them to map out what's going on around the black hole. And what I realized is, as I was looking at these little peaks and the way they lined up, the different times they appeared, first in the blue shift shorter wavelength side of the iron line, and then appearing later in the more redshifted line, is that they line up with the response that we expect to see in our theoretical model of reflection from the disk.
So lower wavelengths at lower frequencies, is that what's going on?
Yeah, exactly right. So we can think about this. I mean, this is the reflection coming off the gas that's on the far side of the black hole to us. So we've got this disk of gas that's around the black hole, and we're seeing the echo coming from this bit of gas that's hidden behind the black hole. And the light from this bit of gas can't travel through the black hole to get to us, because any light that goes into the black hole can't come out. But because of the way the space is warped around the black hole, this emission gets bent around the black hole, and it gets redshifted as it travels close to the black hole, because the waves get stretched out, and it gets delayed just by the time it takes to travel around the black hole as well.
So by combining again that, not only that time delay, but that specific energy shift to very long redshifts, we can be pretty certain that we're seeing something that hit the back of the accretion disk and was wrapped around very close to the black hole before coming to our telescope. Is that fair?
Exactly right. So you can kind of think about this. We've got these two bits of information we can put together. The specific wavelength of the emission tells us whereabouts on the disk it came from. And then the time delay tells us how long the flare took to get from the corona to that bit of the disk and then to our telescope.
Makes sense.
So by putting all of that information together, that's what's letting us build up this map of what's going on just outside the black hole.
Amazing. Really, really, really interesting stuff. So how do these results build on what we've seen before? Because I remember seeing back in 2020 a similar analysis on, I think it was XMM Newton data, where we were seeing these light. Maybe you were involved in it, to be honest. I didn't check the authors. Where we were seeing these reverberations from the disk. Is the new step we've taken here that this is the first time we've seen that sort of full lap being done by light? Is that the new physics we're seeing here?
Yes, that's right. So yeah, the study you're talking about, I was actually a co-author on that. It was led by my colleague, Dr. Will Alston.
That's right.
Who was also previously based at Cambridge. And so we've actually been looking for these echoes of light coming off of the gas falling into the black hole for quite a while now. I mean, these first models of how the flare should be reflected and this bright flash of the echo coming from behind the black hole can actually be traced back to Professor Chris Reynolds, another colleague of mine who came up with these ideas first in the late 90s, but sort of figured it's probably something we wouldn't be able to see until the next generation of X-ray telescopes that we haven't even launched yet And then in about 2009, Phil Utley and Abdu Zogby and Andy Fabian realized that actually, yes, we can start to measure this time delay between the corona and the ion line coming from the disk. And that was really what set my PhD in motion, figuring out how we can use this time delay and the shape of the ion line in the spectrum to actually create this map of the corona.
So we've probably been seeing this light for a long time, but we've never been able until now to be able to specifically separate out those peaks and say, look, this is what we're seeing, and these peaks are due to that wrapping around of the light around the black hole. Is that fair that that's a new step?
Exactly, yeah. I mean, it's almost certainly been there. I mean, all the way back to the first ever measurement of this ion line reflected from a disk made in 1995. I mean, some of that light will have come from behind the black hole. Every time we've measured X-ray echoes, there have been some of that light coming from behind the black hole. I mean, even the beautiful image of the black hole in M87 of the Event Horizon Telescope produced, which showed the shadow of the black hole with the emission from the ring of hot gas around it. Some of the emission in that ring will have done a lap around the black hole, that mostly in the plane of the image they were showing, but also some of it from actually behind the black hole there. Yeah. It's just difficult.
It's all smushed up together, so we don't know where the photons were coming from.
Yeah. It's difficult to say, actually, yes, this signal from behind the black hole is definitely there, and it's even needed to explain the image we're seeing. But now we're actually able to use the time delay information. It's having the time delay as well as the energy shift here that really tells us, yes, this is the emission coming from all the way behind the black hole. So we're seeing light being bent all the way from the far side of the black hole right the way around the black hole for us to see.
Amazing. So as we sort of come to the end of this, the question comes up that what is the value of this research going forward? So obviously it's incredibly fascinating and interesting just on its own accord. But how can we use this information going further? Is it about mapping out that environment around these supermassive black holes? Because it strikes me it's almost like a LiDAR system, right? You've got this lamp that's hanging above, and it's allowing you to bounce light off and get information about that environment. And now we're seeing that we can even get information about the backside simultaneously. Is that the hope going forwards?
Yeah, I think that's the biggest interest for me. I mean, there's been a lot of interest in the media sort of saying headlines like, oh, Einstein was right again.
They always do that. I think it was in the second line underneath. It's always the catch, the hook for the media piece, right? Because
I mean, Einstein's theory, Einstein predicted that light should be bent around massive objects. It actually predated his publication of general relativity. He published a paper in German in 1911 that actually predicted bending of light around massive objects. And Einstein himself, along with Arthur Eddington, observed the bending of light around the sun in 1919. So they'd already confirmed that light is bent by massive objects.
And we've been doing gravitational lensing and things like this for a while now as well.
Yeah, we've been doing gravitational lensing. I mean, gravitational lensing isn't even just a discovery anymore. Gravitational lensing has become a tool for measuring the structure and the expansion of our universe. I mean, we know light gets bent around massive objects. It's just now we're pushing that theory to the real limit. We're showing that it still works when you're in the really strong gravitational field just outside a black hole. And we don't need to make any corrections to GR, as far as we know, even in that limit just outside the event horizon.
So even in those most extreme of environments, the theory still seems to hold up pretty well.
Yeah. But yeah, as you said, I think for me and my colleagues, the really exciting thing here is that we can map out what's going on around the black hole. And this is really important because the Event Horizon Telescope produced that beautiful image of M87. And it can also resolve the Event Horizon in Sagittarius A star, the black hole in the center of our own galaxy. But pretty much every other supermassive black hole is too far away for even the Event Horizon Telescope to be able to get an image of the event horizon itself. Yeah. And just the other week, they produced beautiful images of the very inner regions of jets coming from black holes. And there's an amazing number of things they can do. But in terms of actually resolving the event horizon and what's happening just outside the event horizon, we really are limited to just those two nearby black holes. But looking at these X-ray echoes, it's giving us a whole new way of probing the extreme environment around the black hole, understanding exactly what happens to gas in its final moments, understanding how the corona forms, how black holes power the brightest light sources in the universe, and how, as I said, the thing that got me started on this in the first place, eventually seeing hopefully where the jets come from. And by using these X-ray echoes, we can reconstruct this picture and this map of supermassive black holes, essentially as far away in our universe as we can collect enough photons from. At the moment, we're looking at the nearby galaxies, but we're hoping with the next generation of X-ray telescopes that we'll be able to push this to right back to some of the big bright quasars that are much further away.
And as we close, we can just talk about that sort of future for the research. I guess there's no reason, I can't think of one as a physicist, why the back should be different to the front. You didn't say that, it doesn't say made by God on the back of these things or anything. It's, we have been waiting for you, humanity. I can't think of any reason there'd be a preferred direction that the back is any different from the front.
Yeah, it's the back looks pretty similar to the front from what we've seen. But it's sort of this proof of concept that we can really start to create this map. We can separate the back out from the front and hopefully turn this into a full image. Into
a full sort of radially in at least 2-dimensional image, 3-dimensional image. So the next question, I guess, comes for the future of your research. Is the intention to turn this model to other supermassive black holes that we're aware of and test that it holds up there as well? Are there any other candidates that spring to mind?
We've got a handful of, we've probably got about 10 to 15 supermassive black holes that we've got really strong signals of these X-ray echoes coming from. So those are really prime candidates for looking for similar behavior here. And we're hoping not just to look for the echoes again, but also to really get a deep understanding of what's driving that corona, why those X-ray flares are even being launched in the first place. And saying that, we're just scraping the surface of this Wiki 1 observation. Our work's carrying on to really dig into the corona and everything else that's going on around that fascinating black hole.
And I believe as we sort of push this out into the sort of near to mid future, there's another telescope or observatory that's coming online with Athena.
Exactly right. Yeah. So Athena is the next flagship X-ray observatory. This is a €3 billion mission. Led by the European Space Agency. There's a contribution from NASA here in the United States, and the team I work in at Stanford is actually part of that NASA contribution, developing the detector for Athena. And Athena will be the biggest X-ray telescope we've ever launched. And just by having a bigger mirror, it means it can collect many more photons. And that gives us a much more detailed view, a much more precise view of these supermassive black holes, so that we can really push our models to the limit here.
Is there any idea of the timescales with when we might see that go online?
So we're hoping to get Athena off the ground in 2032, 2033 as the current estimated launch date.
Okay, so there's a lot to look forward to in this field, and these measurements will continue and only get more and more precise. So fascinating stuff. Professor Wilkins, thank you so much for taking the time this morning to chat to me. I've learned so much. Really, really fascinating area of research, and congratulations again on getting out this fascinating paper. Where can people go to keep up with the work that you're doing and find out what's going on from Stanford and going on with this research?
So we have a couple of different outlets that I communicate on. So I've got my own website where I post updates of my research, both for the public and for a more technical audience. That's danwilkins.net. And I'm on Twitter as well, Dr. Dan Wilkins. And then at Stanford, we have got a whole series that actually I've been running over the last couple of years of public lectures where we have members of our department and guests come and give talks about their research to the public at kipac.stanford.edu.
Amazing. I'll make sure that all of those links are down in the description. So head over there, check this out, because it really is fascinating and cutting edge research, and you won't regret it. Professor Wilkins, again, thank you so much for taking the time. I really appreciate it. I'm going to try and turn this research into a nice little mini documentary by the end of the week. So hopefully we can have a very quick chat offline about that when I stop the stream. But
sure.
Thank you very much, everyone, for stopping by. I hope you enjoyed it. I certainly did. And